Hi, everyone. Thank you for joining for another Magnetosphere seminar. It's my pleasure to introduce today's speaker, Eric Grimes. Eric is a programmer, analyst at the UCLA. He works at the Institute of Geophysics and Planetary Physics. Eric specializes in scientific software development in dynamically typed interpreted programming languages such as IDL and Python. And today he will give a tutorial on pySPEDAS. Most of us are familiar with SPEDAS, Space Physics Environment Data Analysis Software. And pySPEDAS is an implementation of the SPEDAS framework in Python. In this tutorial, Eric will give an overview of the pySPEDAS project and show examples of loading and plotting data from several NASA heliophysics missions. Just like Kyle reminded you all, this presentation is recorded, so please keep your microphones muted and switch off your videos. If you have questions, please send them to me on private chat, or you can post them on the group chat, and I'll try to ask them at the end. Thank you very much, Eric, for agreeing to give this presentation. Please go ahead when you're ready.
All right, thanks for having me. So first I should point to the presentation online so that you can all go and check it out later. So to find the PDF online, just go to spedas.org. It should take you to this page here and click on the SPEDAS wiki. And down at under the introduction, there's a SPEDAS presentations link. So click on that. And right at the top, it's Introduction to pySPEDAS 1.0. And that should take you to the PDF. And most of the examples are shared in a Jupyter notebook on our GitHub page. So it's, and to get to our GitHub page, it's github.com/SPEDAS. And there are several projects under there. One is the IDL bleeding edge that's just mirrored. And then there's the pySPEDAS code. And then there's pySPEDAS underscore examples. There's also a repo for MMS examples specifically. So this Jupyter notebook can be found under pySPEDAS examples, and then pySPEDAS examples, tutorials, and it's pySPEDAS 1.0 tutorial. And right now it has dry run in it, but you can ignore that in the name. And so all the examples that we cover should be in this Jupyter notebook. And you can find other examples here as well. And if you're particularly interested in MMS, I showed this. We have a lot of Jupyter notebooks specifically for MMS. And if you click on the images in the README, it should take you to a Jupyter notebook that produces that image. So for instance, we'll click on the SCM image here, and it shows, so it takes you directly to a Jupyter notebook that shows how to calculate that, or actually create those plots. And so let me go ahead and go to full screen. Right, and I have my email on the first page here. It's just egrimes@igpp.ucla.edu. And feel free to email me questions. I'm not going to be checking my email during the presentation, but after the presentation, feel free to email me anytime. And if you have trouble finding this, but you remember my name, Eric Grimes, ericgrimes@ucla.edu also works. It goes to the same place. So for an overview, I'm going to give a brief introduction. Then we're going to talk about projects supported by pySPEDAS. Then I'm going to talk about getting started with pySPEDAS and show some examples. And then we're going to talk about getting help and how to contribute. So for the introduction, pySPEDAS requires Python 3.5 or later, and it depends heavily on pytplot, which was developed at LASP. And we're doing, as I mentioned earlier, we're doing all development on GitHub, and it's just github.com/speedas/pySPEDAS. And if you have questions about the instruments supported or their names or of the functions, see the READMEs on GitHub. So for instance, let's go to GitHub. SPEEDAS. So in the top level README, this is just that link, SPEEDAS/pySPEDAS. We have some information on the project, and then each project supported has a link that goes to the README for that project. So if you're interested in, say, Van Allen probes, you just click on that and it takes you to the README and tells you the instruments that are supported, and then gives some examples of how to actually load the data for each instrument. Back to full screen. So for the project supported, we have ACE, we have a preliminary ERG, it's a ROSE data, and we have cluster data, and that's cluster data loaded from the SPDF. We have SWE, Discover, Equator S, BASS, Geotail, some initial GOES data. I think it's mostly magnetic field at the moment. Image data, so that's the ENA data. And we have MAVEN, MICA, which is a magnetic induction coil array. That's ground mag data. We have MMS, Omni, POSE, Polar, Parker Solar Probe, RBSP, Stereo, Themis, Twins, this is also ENA data, and Ulysses, and some wind data. And one thing to note is that some of these projects have a much higher fidelity than others. If you're familiar with SPEEDAS and IDL, we have a lot of post-processing and pre-processing that occurs in a lot of our missions. And some of that hasn't actually been moved over for many of these missions. I think MMS is really the furthest along. For MMS, we almost have the exact same post-processing codes as we do in IDL. So for instance, we can load the MMS FEEPS omnidirectional energy spectra, which has all the same corrections as in IDL. We also have the EIS omnidirectional energy spectra, and we have the FEEPS and the EIS pitch angle distributions, and it's all almost a direct translation of the code. On the other hand, and for instance, for MAVEN and IDL, we have, I think, around 120,000 lines of code. So not all the bells and whistles for MAVEN have been moved over. Same with Themis. We have a lot of post-processing code for Themis and IDL that hasn't been moved over yet. So for getting started, I'm going to talk about actually installing Anaconda, because we suggest using Anaconda to actually get Python installed on your machine. I'm going to talk about virtual environments and installing pySPEDAS, and then setting your local data directories. So for installing Anaconda, there are step-by-step instructions on their website, and I included links for each operating system here. So these include images that actually show you step-by-step how to get started. And of course, if you have any trouble getting started with Anaconda, feel free to email me. And once Anaconda is installed, you should be able to open Python in your terminal window just by typing Python. And your Python version should be on the first line displayed. So for instance, in my terminal, I just typed Python, and I was running Python 3.7.2. And to avoid potential dependency issues with other Python packages, it's usually best to create a virtual environment in Python. We require some, well, pytplot requires some very specific dependencies. So if to avoid problems when you're upgrading other packages or installing other packages, I really suggest using virtual environments. And you can create a virtual environment in your terminal with just python -m v e and v, and then give it the environment name And then you enter the virtual environment by running the activate script. So on Mac OS and Linux, it's just you type source, the environment name, /bin/activate. And on Windows, it's just / the environment name, scripts, and then activate. And so, for example, down here at the bottom, I created a virtual environment called pySPEDAS-stuff, and I just called Python -mv pySPEDAS-stuff. And then since I was running on Mac, I typed source pySPEDAS-stuff /bin activate. And you can see over here on the left of the terminal, it included in parentheses pySPEDAS-stuff. And so when you run Python, after running the source command, it should open Python in this virtual environment. And what that does is isolate your dependencies, it creates an isolated environment for you to install pySPEDAS. So once you're in that virtual environment, the first time you enter the virtual environment, you'll have to install pySPEDAS. So this is just as simple as pip install pySPEDAS. And this should go out and find all the required libraries and install them inside the virtual environment. And if you want to upgrade your copy of pySPEDAS inside the virtual environment, it's pip install pySPEDAS -- upgrade. So if you do pip install pySPEDAS, but you already have pySPEDAS installed, it actually won't get the latest version. So you'll have to do a -- upgrade to actually get the latest version. And for setting your local data directories, we use environment variables. So we support the SPEDAS data dir environment variable that points to the top level directory for all of the missions and instruments. And each mission also has its own data directory, for instance, MMS_data dir, and this is for MMS, and then them_data dir for themis. And an important note is that the mission data directories will override the root data directory set by SPEDAS data dir. So if you set MMS data dir, it'll prefer that over the SPEDAS data dir. And these, if you're using the latest SPEDAS bleeding edge, SPEDAS data dir should also be supported there as well. So you can now share data between IDL and Python simply by setting this as your data directory. So once you're in your virtual environment, running pySPEDAS is simply just a matter of running Python. You type Python, and then you type inside the Python interpreter, you just type import pySPEDAS. And you can access the load routines. So the load routines are pySPEDAS.mission.instrument. And those are functions that actually go out and load the data into pytplot variables. So you can also access the load routines by importing the mission modules directly. So you can say from pySPEDAS import MMS, themis, and cluster, and that'll give you access to the MMS, themis, and cluster modules. You could also import the instrument load routines from the mission modules specifically. So you can, for instance, you can say from pySPEDAS.mms import FGM and FPI. So those import the FGM function and the FPI function. And from pySPEDAS themis import ESA and SSD. Although this probably isn't the best way of going about it, since themis also has an FGM function. You're going to get your namespaces mixed up here. So the preferred way is probably just to call pySPEDAS.mission.instrument, which most of the examples will show have that. So for just getting started loading some MMS Fluxgate data. So what I did here is just copy and paste my the terminal window from loading some data. So at the top, you can see I said data equals pySPEDAS.mms.fgm. And then I set the T range keyword, set the time range, and I specified 6 hours of data. And I set the time clip keyword to true. So it actually time clips down to the 6 hours of data. And another thing to note is that if you don't specify any keywords, it should load some default data just by default. But I wanted to actually show how to specify keywords as well here. And you can see it, so it loaded the data locally, but that's because I had the data already stored, the data file already stored. If you don't have the data file already stored, it goes out to the SDC and it downloads the data to your local data directories. And so the MMS load routines also have a bunch of other, or most of the instrument load routines actually have a bunch of other keywords that we're not showing. For instance, the data rate, by default, it loads survey mode data, but you can also specify burst mode. And by default, it loads L2 data, but there's a level keyword that allows you to specify other levels. And there's also, for MMS, there's an SPDF keyword that you set to true, and it'll load the data from the SPDF instead of the SDC at LASP. But for this case, we just only specify the time range and the time clip to time clip it down to 6 hours of data. And you can see that it told you the loaded variables, and it time clipped those variables. And one thing to note is that note that I had data equals, and so this function actually returns a list of the tplot variable names that were created. So to create a plot, you just call or import the tplot function from pytplot. So it's just from pytplot import tplot, and then just like an IDL, you call tplot on the variable names. And it supports a string or an array of strings. So you can say tplot and then give it an array showing the GSC variable name and the GSM variable name. And here's a copy of the figure that's created. You can see that GSC data is on top and the GSM data is on bottom. And it's 6 hours of data since we had the time clip keyword earlier. And another thing to note for MMS, the default is probe 1. It loads probe 1, but there's also a probe keyword that'll allow you to load a different probe or multiple probes at once, just by specifying the probe. So if you wanted to load probe 3, just in the arguments, you just say comma probe 3. So for loading FPI data, it's the same thing, just pySPEDAS.mms.fpi. In this case, we're loading burst mode data, 1 minute of burst mode data. So I set the time range to 1 minute on October 16th, 2015. And I specify the data rate as burst. And I set the data type to DES moms. This is the electron moments for FPI. And you can see it downloaded the data. Since I didn't have that locally already, it went out and downloaded it, and then it loaded it into variables. And I clipped it down here at the bottom since the list of variables was pretty long. But to create a plot, you just do, just like with the FGM data, you call tplot on the variable names that you want to plot. So in this case, we're plotting the omnidirectional energy spectra, the perpendicular energy spectra, and the parallel energy spectra for electrons. And this is the figure it creates. And an important thing to note is that while the color bars look very similar to IDL here, they are slightly different. So I think there's more blue and more black in IDL. So it's they look very similar, but not exact. So what if you want to find all the variables that you've loaded so far? You just import tplot underscore names from pytplot, and it has the same name as the function that we use in IDL. So you just call pytplot or tplot underscore names, and it'll list all the variable names that are currently loaded in memory. So I ran it after creating those two plots, and you can see that it showed the FGM variables as well as the DES variables that are loaded. And I clipped it down here at the bottom because the variable list was too long to show on a single slide. And another thing to note is that this function actually also returns the variable names So the return value of this function is the variable names. So if you set, say, data equals tplot underscore names, and data will actually contain the variable names. And just like an IDL, there are numbers associated with each variable name that you can call in tplot in your tplot function. So if you don't want to type out the full variable name, you could just specify the numbers instead. So another example from a different mission, to load SCM data. That's the search coil magnetometer data from Themis. You just call pySPEDAS.themis.scm. You could set the T range keyword and the probe keyword. And since I already had the data file locally, it just loaded that local data file. But if you don't have it, it goes out and downloads the data from Berkeley. And if you do have it, it'll check it actually checks to make sure it's the latest version. So if a new version is out there, it'll go out and download the new version instead of loading the version you have. And you can see it returned the variable names that it loaded. And I went ahead and created the plot. So I called tplot on the GSE SCF data, and then and also the GSM data. And so I mentioned earlier that we don't have all of the post-processing. So some of that is actually setting the metadata for data types. So in this example, you can notice that there isn't a Y title and there aren't labels and the colors are different. By default, pytplot, when it plots a vector, I think the Z is green instead of red in our standard color system. So to update the plot metadata, you just like with tplot, you import options from pytplot. So it's from pytplot import options. And so in this bottom panel, I showed what happens when you call the help function on options. And that's usually how I figure out what options are available and how to set them. So I just called help on this options function and got all the options. So to change the color, you just set the color option. To change the color table, it's color map. And there's a bunch of different color maps. We actually use matplotlib's color maps. You could set this Z log, Y log, and one important thing is legend names. That's the same thing as labels in IDL. So just for instance, setting some options on that SCM data that we loaded earlier, we could set the labels to BX, BY, BZ, along with the coordinate systems by setting the legend names. And then we could set the options, say color, so blue, green, and red. That's our standard colors. Blue for X, green for Y, and red for Z. And we can also limit the Y range on the plots. And then we call tplot on the variables again, and it should update the metadata. So now you can see that the labels have been updated, the colors have been updated, and the Y range is now limited to +20 and -20 for each of the variables. And I didn't show how to set the Y title, but it's just Y title to set that option over here. And eventually we're gonna have all of that set automatically, but we're still working on all the post-processing and pre-processing stuff. So another example, loading RBSP data. So in this case, we loaded, we just called pySPEDAS.RBSP.emphasis, since emphasis is the FGM, the function. So, and I specified the T range. It's just one day on October 16, 2016. And it went out and since we already had the variable loaded or the data file locally, it checked to make sure that it was up to date. And if you don't specify a probe, it loads probe A by default. And it loads the 4-second data and SM coordinates by default. But there's keywords for changing the coordinate system and the data type and the level. And to find those keywords, it's just a matter of calling pySPEDAS or calling help on pySPEDAS.rbsp.emphasis. And you can see the variables it created, mag and magnitude. And so if we call tplot on these variables, it's just tplot on magnitude and mag. So we have the magnitude on top and then the magnetic field vector on the bottom. So I mentioned, so if you want to find the load routine options, it's just a matter of calling help on whatever function you're interested in. So this is the output of calling help on pySPEDAS.rbsp.mag.eis. You can see that we support the T-range keyword, probe, data type, suffix. Will append a suffix to the variables created. Get support data. If you set that to true, it'll load the data in the files with the var type is set to support data. Var format will allow you to only load a subset of the variables in the files. And a lot of these should be very similar to how it works in IDL. Most of our load routines in IDL also support a var format keyword. And you can set the download only keyword to true, and it'll just download the CDF files and not actually load them into memory. And pretty much all of our missions and Python also support a no tplot keyword. So this will return the data in hash tables instead of creating the tplot variables. And we also support a no update. So no update won't go out to the SDC or won't go out to the SPDF to download the files. It'll only load the files if you have them stored locally in your cache. And of course, time clip clips the data down to the actual requested time range. By default, it'll load all the data within the data files that are within your time range. So you might actually get more data than you're expecting if you don't set the time clip keyword to true. And this is just the mag.eis function. If you call this on, you can call this on any of the instrument names. So for instance, if you call it on pySPEDAS.mms.fpi, you'll see a long list of parameters that FPI supports. And the MMS functions mostly or actually support more keywords than most of the other instruments, since that's the highest fidelity mission we have so far. For instance, for FPI on MMS, we have a center underscore measurement keyword that you can set to true. That'll actually center the measurement to the center of the accumulation interval, just like we have in IDL. And by default, the FPI data and the HBCA data and for MMS are actually at the beginning of the accumulation interval. So if you load the MMS, FPI, or HBCA data, you really want to set the center measurement keyword, especially if you're doing calculations with FGM data or multiple instruments, because, for instance, the FGM data are actually at the center of the accumulation interval. So it's important to actually check these keywords to know what the available options are. And so, for instance, remember the download only keyword. In this case, we're calling pySPEDAS.rbsp.mag.eis, and we set the time range to November 5th, 2018, and set the probe to A and B, and we set the download only to true. So in this case, it goes out and makes sure that we have the, since I already had the files locally, it just says file is current. But if I didn't have the files locally, it would download the files, and then it would return the file names. Since we set download only equals true, it didn't load it into tplot variables. It just returned the file names. And we also have discover data. So for in this case, we import the discover mission module from pySPEDAS. I'm just showing here a different way of accessing the data. So we can call from pySPEDAS import discover, and then call discover.mag. So the variable or the function to load the magnetic field data from discover is just called mag. and we set the date or the time range to October 16th, 2016. And you can see it already had the data locally, so it just loaded that local file, and it returned the variable names. And then we also have discover.fc, which is the Faraday cup data. And again, I just set the time range to the same time range as before, and it just loaded the data. And to plot it, I just called tplot, and at first I gave it, or the first variable I gave was the magnetic field and GSC coordinates, and then the velocity and GSC coordinates, and then the number density. And you can see it created the plot with the B field on top, the velocity in the middle, and then the number density down at the bottom. And for Parker Solar Probe, it's a similar thing, just fields vars, we're going to load some fields data. It's pySPEDAS.psp.fields, and they set the time range to November 5th, 2018. And this is only loading 6 hours of data. And I set the data type to MagRTN, which I think is the default data type here, and leveled it to. I wanted to explicitly just show some keywords here, but I think by default that's the data it loads. And you can see it created, it returned a variable, the variable that it loaded. It's just PSP_FLD L2 MagRTN. And so it called tplot on that function, or on that tplot variable. And I think most of the other examples so far have showed a list of variable names. In this case, I just plotted one variable name. So I just called it on the string, and it loaded the data. So for Omni data, it's this is the Omni parameters that are time shifted to the magnetopods. So it's just pySPEDAS.omni.data. You set the time range. So in this case, the time clip keyword is automatic. It automatically sets time clip to true because the Omni data files are monthly. So if you request 1 day of data, if you didn't automatically set the time clip keyword to true, it would load the entire month. So by default, the Omni data actually does time clip the data. And so I called tplot on the Omni variables. So the first 3 panels are Bx, By, and Bz. And then we have the flow speed, and then Vx, Vy, and Bz. So it's the solar wind data, time shifted to the magnetopause, and then SimH is down at the bottom. So what if you actually want to work with the data files or work with the data values instead of creating plots? PyTplot has a function called get_data that works very similar to how we to our get data function in IDL. So you just say bx times, so to get the bx values, it's just bx times and bx values equals get_data and then the variable name. And so the thing to note is that get data returns a tuple with the times and then the values. And the times are stored as Unix times. So this is times since, or seconds since January 1st, 1970. And they should match exactly what they are in IDL. And the bx values are stored as the NumPy array. And so what if you want to work with the times? We have 2 functions that are very similar to how they work in IDL. It's time_string and time_double. And so you just import time_string from pySPEDAS, and that'll convert the Unix times to time strings. And the thing to note is that it works on a single value as well as an array of values. So in this case, I plotted, showed 5 time. I convert the first 5 times to strings. You can see it should be 1 minute apiece, since the Omni data that I loaded was 1 minute resolution data. And if you want to convert back to to Unix times. From the time string, it's just time underscore double, and you import that from pySPEDAS and then call it on the. So at this bottom example, we're calling time string on the Unix times and then converting them back to time doubles. So what about energy spectra? So get data supports that as well. The thing to note is that if there's an extra dimension, that'll be returned as an extra dimension on the tuple. So, so for energy spectra, this is that burst mode DES spectra that we loaded earlier. It's times the data values and then the energy table. So you can see that the times are just a NumPy array containing the Unix times. The data are the actual data values, and then the energies are is the actual energy table. So these are essentially the Y values. And since this is burst mode FPI data, the energy table here is actually time varying. So each time step has a different energy table, and you can see that pySPEDAS supports that time varying energy table. And another thing to note is, say if you have distribution data that's a function of energy and angle, you would have to do times data, energy, and then angle, or comma angle. So it just adds, for every dimension, it just adds another dimension in the tuple returned by get data. And for creating variables, so just like in IDL, we have store underscore data. So you just call from pytplot import store underscore data. And then the first argument in the store underscore data function is the variable name that you want to create. And then you set data equals to, and give it a hash table with, so the X values are the times in Unix times, and the Y values are your data values. If you want to do a spectra, it's you have to have a V tag for the energies. Or if you want a pitch angle distribution, you'll have a V tag for the angles. And so I called store data and created a new variable called bx underscore values, and then I called tplot on that new variable, and this is what was created. So this should be the same as the bx from before. And so the Omni data actually loads the bx, by, and bz components into individual, their own independent variables. So pytplot also has a function called join vec that allows you to create a vector from the individual components. And this is just like an IDL. You call join underscore vec, and you give it an array of the vectors or tplot variables, and then you specify a new tvar name. And so in this case, we're calling it omni underscore b underscore GSC. Then you can call tplot on that variable, and it should plot the vector in one panel. And so you can also split a vector into its components. Just like an IDL, we have split underscore vec. So you call from pytplot import split underscore vec, and call it on the vector name. So, and it creates 3 tplot variables, one x, y, and z. And then we can call tplot on those variables. And it should plot the components in their own panels. And another thing to note is that by default, when you do all of this, it'll create, it creates them with the default metadata from pytplot, which might not be what you want. So you'll have to import options from pytplot and set the options individually after you create these new variables. So we have a lot of examples in the READMEs on GitHub. We also have Jupyter Notebooks on GitHub, and that's just at github.com/speedas. And of course, if you have questions, feel free to email me anytime. It's egrimes@igpp.ucla.edu. And again, my full name, Eric Grimes, @ucla.edu also works if you have trouble finding this one. So how to contribute, I suggest trying it out, and please report bugs, missing documentation, or any other issues so we can fix them. And feel free to email me, or you can submit them through GitHub issues, whatever's easiest for you. You can also, if you have changes or bug fixes that you've made locally, you can also submit them through pull requests on GitHub, or you can email them to me directly and I'll get them in. Again, it's whichever is easiest for you. Or if there's a missing data set or analysis tool that you want to see included, let us know. And so that's pretty much all I have. I guess I should show again how to get to this presentation. It's SPEDAS.org, and then click the SPEDAS wiki. And then under the introduction, it's SPEDAS presentations. And then right there at the top, it's Introduction to pySPEDAS 1.0. And for the Jupyter notebook, it's just go to our GitHub SPEDAS, and then pySPEDAS_examples, and then pySPEDAS examples and tutorials, and it's pySPEDAS 1.0 tutorial. I think all the examples that we covered are actually in here, plus a few extra, like in using the suffix keyword, and there's loading some ENA data from image in here. And for MMS, again, right at the top level, there's an MMS-examples repository with a lot of MMS examples. Like, for instance, calculating the curlometer technique using MMS FGM data. And we also have, PEEPS omnidirectional spectra, and the PEEPS omnidirectional pitch angle distribution, the EIS omnidirectional spectra, and EIS pitch angle distribution. So we have lots and lots of examples. I think you can just click on basic and see all the different Jupyter notebooks, orbit plots and calculating plasma beta with FGM and FPI data. So we have lots of examples, but if you have more suggestions for examples, email me and we can create more of these. So I guess, are there any questions?
Thank you, Eric. Yeah, that was a very great presentation, very clear. Of course, there's a lot of information and people can go to the links that you pointed out, or you can watch the presentation again, the recorded presentation that will be online. We do have some questions. I'm going to start with the first question. That comes from Kyle Murphy. He wants to know if there are documentations on various functions, different data levels, different level types for each mission and instrument.
So right now it's not very good, but the documentation that does exist is primarily in the READMEs. So for instance, MMS. And in the help function. So for instance, let's call help on pySPEDAS.mms.fpi. So this is probably the best place to go, is calling help on the actual function name. But for a lot of the emissions and instruments, it's lacking, and we need to do a better job of actually updating it.
Okay, thank you. The next question is from Eric Lund. He wants to know if there are keywords to load only a certain energy or pitch angle range for particle data.
So it depends on the mission and the instrument. So for the most part, these are essentially just load the data that's in the CDF files. So if the CDF files So for instance, with the FPI data, if you request DES moms, you're going to get the DES mom CDF files. But if there are certain variables in those files that you want to limit, you'll have to specify the var format keyword to limit the variables. But by default, we load all of the data loaded. However, if you say you want to calculate the FEEPS and EIS pitch angle distributions, there are keywords for doing that. So I think it's EIS, actually I think it's pySPEDAS. When you calculate the FEEPS pitch angle distribution, there's a keyword for, say, energy to specify the energies in the calculation. You can also specify the bin size. There's also a keyword to calculate the angles directly from the B field rather than using the angles in the CDFs. So it really just depends on the mission, the instrument, and the format of the CDF files and the data.
Okay. Let's move on to the next question. This comes from Xing Hong. He says he tried to load CDF file created by tplot2 CDF from IDL into Python, and it gives different answer, like it's missing all values. Can it be a problem from how Python and IDL handle CDF files differently?
So I would suggest emailing me the exact case that you tried in that example, because we actually have routines as part of our IDL test suite that loads the data, and IDL loads the data in Python and then checks that the values and the times and everything actually match. So they should be very, very close, if not exact. There might be small precision differences, but our unit test suite for MMS especially actually verifies that they do match for MMS. So if you find a case where they don't match, please send me an email and let me know so that we can look into it, or file an issue on GitHub, whichever's easiest.
Okay, yeah, thank you. So I'm sure he will get in touch with you on that. So the next question is from Jose. And he says, do you have to specify whether the data is given in 2D to plot with pyplot?
So I don't entirely know what I'm not entirely sure I understand the question.
Well, he wants to know if he has to specify whether the data is given in 2D to plot with pytplot. I don't know if that's a specific function. Maybe, I don't know if he's online, he could probably ask the question.
By default, it does plot the data as lines. So if you call it on a function, if the data are spectra, you'll have to call options and set the spectra to true. And again, you can convert, you can turn spectra off and actually plot the individual lines of the spectra. But by default, it just plots the data as lines.
Okay, I have a comment here from Jose. He says he means 3D plot. I don't know if he's online. He can probably unmute himself and ask the question.
I'm online here. Can you hear me?
Yes, we can.
Yeah, I was trying to plot a color map or something like that using those examples, and I got an error because they said the data must be 2D or something like that. I was trying to plot some RBSP data from electron flux.
So it's possible that that variable actually has multiple dimensions.
Yeah, that's true. So I must specify if the data has multiple dimensions, something like that.
So if you send me the example that you're trying to plot, and I can look into it, but I suspect a dimension that it's trying to plot that it can't actually plot. For instance, if you load data that's a function of energy and angle, it's not going to be able to, it's not going to know which to use as the y-axis.
Yeah, that's the problem. I got it. Thank you.
Yep.
Thank you, Jose. One last question from Luis. He's asking if it's possible to plot the CDFs for MMS cluster and Themis parallel and perpendicular to the B field.
So it's a good question. I'm not entirely sure. So I think for MMS, DES has the data stored in the files. And so that's the variable names that are.
I think he means velocity distribution function rather than
no. So we don't have
CDF.
Yeah, unfortunately, we don't have functions for plotting the distribution functions yet, or really working with the distribution functions. It is something that we want to work on in the future. But
okay.
We have a lot of legacy codes in IDL to actually do that haven't been moved over yet. But it is on the roadmap, and we're hoping to get to that soon.
Okay, so one last question, that's from Ben. He wants to know if the figures look like you're using a backend other than Matplotlib, except in a few specific areas. What was the reason behind this?
So yeah, we use pyQt graph behind pytplot. And I think the reason originally was speed. But we do, I hope that eventually we can go back to Matplotlib and look into why that was so slow. I think some of these data types actually have a lot of data actually in them. Because it's, for instance, for MMS, it's very high resolution. And so creating a plot can take a long time if you use the wrong backend. But I would actually like to go back and see if we can figure out how to use Matplotlib, because there's a much larger community for Matplotlib. And I know that you can change the backend from Matplotlib to pyQt graph, which is what we're using. So that's the best answer I think I can give. But the pytplot people probably have more details, since they were the ones who actually implemented the the tplot function.
Okay, yeah, thank you. That was a great presentation. Thank you for your time. Thank you for the presentation. If people have more questions, you can email Eric or look back at the presentation, a recorded presentation. Before everyone goes, I would like to remind you of our talk next week. Please join us again at the same time. Herman Lua will talk about magnetospheric field-aligned currents, their signatures in the ionosphere. So thank you all for joining, and thank you so much, Eric, for the great presentation.